Hey everyone, I'm Angela. I'll be talking to you about earth science today. So this little quick self-introduction. As you can tell, this is me. Okay, so I don't actually have much experience in science school, but before you come at me, I'm just here to teach you earth science. So actually, in 7th grade, I did science bowl for a few months, and I was in charge of earth science as well. But I quit because it just wasn't right for me. But here are some of my other qualifications. So I've been doing science Olympiad since 6th grade, and I've been doing either fossils or rocks and minerals basically every year. So I'll be talking about rocks and minerals today. So if I talk too much about that, then you know why. And I've also been to the USSU junior camp. So basically I flew over to Vermont and I just did some field work, and I got to study some environmental issues. And I had to present on like the interactions of the Earth's spheres, which I'll be going over in the next slide. There we go. So this is like a very nice aesthetic diagram. Don't worry if you can't read anything, because I'm not actually going to talk about it. I just chose this diagram because it looked nice. So in this diagram, there are 5 different spheres of the Earth, and that just shows like different categories of earth science, essentially. So you can see there's the atmosphere, as y'all know, like air stuff, and cryosphere for ice, biosphere for life, geosphere, and this is also known as the lithosphere for solid earth, and hydrosphere for water. And then there's also a 6th sphere that some people consider, and that's called the anthroposphere, also known as like the human sphere, because anthropo means human. And that's just because humans have had such a big impact on the world that people are considering it a separate sphere. So basically, this is a general overview of earth science as a whole, and I'll be going more into depth about these 4 topics. Okay. And then, so first up, we have rocks and minerals. So for those of you who are curious, this background is amethyst. That's a type of quartz, and it's also the birthstone of February. So if anyone's born in February, then shout out to you, I guess. Okay, so what is a mineral? So I have a snowflake here and an ice cube here, or multiple ice cubes, multiple snowflakes. So I'm gonna bring up a poll. Let's see. Yeah, which of the following do you think is a mineral, or both, or neither? Okay, so it's about 140. Okay, people are still voting. I'll wait until 35, and then I'll end it. Okay, I'm gonna end the poll now. So, okay, I'm gonna share the results. So most of you guys put neither. So I will not answer the question correctly yet because I want you guys to pay attention. So here. So there are 5 main characteristics of a mineral. It has to be solid, naturally occurring, as in it can't be man-made. Has to have an ordered atomic structure, which usually means it's crystalline. And so like the atoms are just aligned really nicely. And minerals are inorganic, so they're not produced by living things or related really in any way. And they also have a definite composition or a range of compositions. So if you had 2 samples of the same mineral, they should be made up of the same atoms. And for ordered atomic structure, I put some crystal systems here. They're just ways to differentiate different types of crystals. So these little lines connect the faces of the crystal. And then there's also definitions for the angles and which category this would belong in. So I'll talk about this a little more in the next slide too. Okay, so back to the ice question. So this is like a really weird nuance. So the snowflake is naturally occurring and also fits all of these other things. So it's actually considered but because ice is not naturally, the ice cubes is not naturally occurring because it's man-made, this would not be considered a mineral. So that's just kind of weird, but that's a thing. Okay, so mineral properties. Okay, yes, that is a pet rock from earlier, for those wondering. There are a few main properties that are pretty important. So first one I'll go over is hardness. So this scale over here is called the Mohs hardness scale. So it goes from 1 through 10, and as the numbers increase, then the hardness increases. So all of these minerals here are like pretty representative of this value. So whatever Mohs hardness scale you search up, it should probably be these same minerals. And what the hardness means is that if you have a harder mineral, and you can scratch a softer mineral. And over here you can see there's fingernail, copper coin, knife, and steel. And so all of these can scratch the minerals that are before it. So for example, your fingernail can scratch both. And also if you take a look here, diamond is the hardest mineral, but that does not mean it's like indestructible. So you can actually break it using force and not necessarily scratch it. So I will talk about this when I get to this point, cleavage and fracture. Okay, so first I'll talk about luster. So that's basically how the mineral looks when you shine light. So there's metallic and non-metallic luster. So it's kind of self-explanatory, like metallic minerals look like metal and shiny like metal, and non-metallic minerals don't. And non-metallic can be split into other categories and that are also pretty self-explanatory. So for example, we can have earthy, so that's like dull and earthy looking, and pearly or vitreous, and vitreous means glassy because of the prefix like vitro, that means glass. And there's other there are other lusters that are similarly named. And next main property would be streak. So streak is the color of the powdered mineral. And how you would find it is you would take a plate of unglazed porcelain. So it's kind of like rough, not really, but kind of. And you would scratch the mineral on that porcelain, and that would be called a streak plate. And the color that the mineral leaves behind would be the streak. And the streak is actually a better way of identifying a mineral compared to its color, because the same mineral can have like a variety of colors, but it usually will have the same streak. Okay, and then on to cleavage and fracture. So back to that diamond thing I said earlier. So cleavage is when a mineral has planes of weakness. So when you put a force on it, it will tend to break along those planes of weakness. So this here is biotite mica. It's pretty famous for its perfect cleavage, and it cleaves into these really nice little plates kind of things. And so back to diamond, even though diamond is the hardest mineral, it still has cleavage. So if you put force on it in a certain way, it will still break. So that's something to note. And fracture is when a mineral doesn't have specific planes of weakness, so it will tend to break more unevenly. Sometimes you can see in quartz, it breaks in like really weird, wiggly, wavy lines. And I don't have a picture, which is kind of sad. Okay. And then next I'll be going over crystal system and habit. So if you remember from earlier, okay, here, okay. This is, these are the crystal systems. So they're how the crystals would grow normally. And over here are the crystal habits. I'm not going to talk about each one in detail, but you can just feel free to take a look at it. So crystal habit is how the crystal, like how the mineral outwardly looks. So it can grow in a bunch of different weird shapes, like you can see fibrous, and like they're not necessarily those perfect, pretty looking crystals from over here. So this would be what you would see like out in the field, whereas this would be, this is more of a definition of the mineral because it depends on the angles of the faces. It's not necessarily that the mineral is going to look just like this. So that's a little difference I'd like to note. In specific gravity, someone asked about this. Okay, I'll just explain it first. Specific gravity is also known as relative density. So you would find it by dividing the density of the mineral with that of water. So that just, yeah, it's just like a weird way to denote this. So that basically means that the specific gravity doesn't have a unit, a convention for. You can also do relative density compared to other things, but that just doesn't really apply in this case because mineralogists are weird, right? Okay, so onto the important ores. So an ore is when there's a deposit in a sediment of a large amount of mineral or metal that is valuable and can be mined for profit. So as you can see, diagram, these are all the important ores you'll need to know. For example, you have coal, diamond. Okay, these are actually like real things, okay, not ones. That's just weird. Oh, whoops. And yes, emerald is green. Okay, sorry for the Minecraft. Okay, onto the actual slide. So these are just a few ores I've selected that I felt were pretty important, and like test writers like to ask about them in Science Bowl, and also like in Science or other earth science tests. So this is kind of just memorization, but I won't like force this on you. So I'll just talk about each of them, and hopefully you can remember something from this. So over here, this is bauxite. This is an ore of aluminum, and it looks kind of weird. Like it has these little rings on it called pisolites, and that's just something that's pretty notable about this. And next ore would be magnetite and hematite as ores of iron. Those are pretty famous. So magnetite, as you may expect, magnetite is magnetic, but not necessarily magnetic in the sense that it attracts other things, but it can be attracted by a magnet, and you can magnetize it. So I think this is called being ferromagnetic, but I'm not a physicist, so don't come at me. And hematite is apparently also magnetic in a different way. But the most notable thing about it is that even though outwardly it looks like brownish, blackish, its streak is red, so that's a key way of identifying it. And if you guys are familiar with heme or hemoglobin in blood, yeah, this little prefix means blood. So and the streak of this is blood red. And if you also remember, heme is an iron carrying component in blood. So that kind of like connects there. That's a way to remember this. And next, whoops. Okay, next we'll be talking about cinnamon or mercury, which is this over here. It actually looks really nice, and you can wear it as jewelry, which is kind of weird if you think about it, because mercury is like pretty toxic. But the reason why it's safe to wear as jewelry is because, first of all, you're wearing it, you're not eating it, so it's pretty hard to get into your body in the first place. And also, the way this mineral is, you can swallow a crystal, and it would be very hard for the mercury to actually get into your blood. But also, don't swallow a crystal, because yeah, just you might die, so that's not good. And then just this thing, this is an ore of lead. So it has a really cool looking crystal shape. So it's very nicely cubic. And as you might expect from lead, it has a very high specific gravity. So if you get a really tiny piece, it's actually unexpectedly heavy. So I would recommend you try to get your hands on some and feel it, but also don't eat it, because I don't want you to die. Yeah, okay. Sphalerite next is an ore of zinc. I didn't put a picture of it, similar to magnetite and hematite, because it looks kind of boring. It kind of just looks like black crystals. It's not very notable, so I'll move on. Lastly, we have chalcocite, chalcopyrite, and bornite as ores of copper. So over here, this is bornite. It's also known as peacock ore because it looks like peacock colored-ish, so it's iridescent, and people buy this just because it looks nice. And there's scandals, not scandals, with chalcopyrite, because you can treat it with acid and you can make fake peacock ore from it. So that's interesting. And chalcopyrite, as you might think from the pyrite in it, looks kind of like pyrite, so it's yellowish, goldish. And pyrite is fool's gold, so chalcopyrite also looks similar. But pyrite actually looks pretty different from gold, because the color is just completely off, and the crystals are usually cubic or something octahedral, something like that. So the crystals of pyrite actually look similar to this. That's very unlike gold. Okay. Next topic would be rocks. So rocks are just a bunch of minerals like that are stuck together in some way, and so they don't necessarily have the exact same composition. So that's what makes them not minerals. So yeah. And there are three main categories of rocks. You have igneous, sedimentary, and metamorphic. And you can see this is the rock cycle. I'm sure most of you guys are familiar with this. I won't be talking about this too much, but it basically just shows the connections between all of the types of rock. So it's not just a one cycle, like each type can be converted into the other type. So first for igneous rocks, they can be, okay, igneous rocks are formed from the cooling of magma or lava. So that's just molten rock, essentially. And there are two main types. It's called intrusive and extrusive. So intrusive igneous rocks cool beneath the Earth's surface. So they tend to cool more slowly, and that gives them the time for crystals to form. So in this picture, this is granite. So granite, you can see it has visible crystals. So that's what tells you that it's intrusive. And then extrusive igneous rocks cool above the Earth's surface. So because it's a lot colder than inside, they cool a lot faster. And so the crystals can't usually be seen because they are so small. So this is basalt. You can see, or you can't see the crystals. And that's what tells you that it is an extrusive rock. There's also mafic versus felsic. That's another way of differentiating igneous rocks. So mafic, if you like split it up, like split it down the middle. So the Ma is for magnesium and the Fic is for like ferric, so iron. So mafic rocks are rich in magnesium and iron, makes them dark in color. So this is, and felsic is rich in feldspar, which is from this first part, and quartz, or also known as silica, so this is the second part. And feldspar is this pinkish mineral, and is usually commonly clear, or it can be other colors, but in general, both of them are light colored. So this granite is felsic because it is light colored. And sedimentary rocks, so they are the ones that contain fossils mostly, because they're formed from sediments that get piled on top of each other. And so when an organism dies and it gets buried by the sediment, it's mostly like left unmodified and nothing really happens to it, so it can get preserved as a fossil. Whereas other types of rock, they undergo a lot. So for example, igneous rocks have to melt, or they form from molten rock. So another type of rock has to melt first, and that usually can destroy any organisms that were stuck in there. And then last type of rock would be metamorphic. So this can be split into foliated and non-foliated. So foliated just means that there are lines and layers that you can visibly see. So metamorphic rocks form when heat and pressure is applied on another type of rock, or even another metamorphic rock. And the foliations form when the pressure is in a certain direction, and that can make it layered. So you can see in this little chain here, you start with shale, which is a sedimentary rock, and you can put increasing amounts of heat and pressure, and it can actually change into multiple different types of metamorphic rock, and it finally gets to this nice piece of gneiss. Right, okay. And back to this rock cycle, this kind of just shows how like any other thing can connect into and form into something else. And for weathering, weathering is when like a rock is kind of like sediments are removed from the rock, so it's kind of like rubbed. And then erosion is when the sediments are actually transported, and this transport can eventually form sedimentary rocks. So next main